Hey guys, this is some visual video to go along with chapter 3 about electromagnetic radiation. So one of the first things I wanted to show you guys is the difference between wavelength and frequency and how those correlate to each other. So with wavelength, if we look at this first photon representation, anytime you see it in waveform like this, it's a photon, meaning it's the smallest unit of electromagnetic energy. Okay, so wavelength is the distance between any two successive points on a wave. So you can go peak to peak, or you could measure valley to valley. So if we call this the wavelength and this the wavelength of B, you can see that the wavelength of A is shorter than the wavelength of B. So with A, it has a decreased wavelength, and B has an increased wavelength. And then if we look at frequency, it's the number of times the wave passes in a given cycle. So let's just make the whole thing this cycle. In this one, there's one wave, 2, 3, 4. So that has 4. This one has 1, 2, 3. So this one has an increased frequency. This one would have a decreased frequency. And if you look, the relationship between frequency and wavelength is inverse, meaning if the wavelength gets longer, the frequency goes down. And if the wavelength gets shorter, the frequency increases. Okay? Another interesting thing is the correlation between frequency and energy, because frequency and energy are directly related. So frequency and energy have a direct relationship, meaning if one goes up, the other goes up. And if one goes down, the other goes down. So if we look at these with regard to energy, this one has a higher frequency. This one also has more energy, meaning it's more penetrating than this one. Okay, so higher frequency, higher energy. So increased frequency, increased energy, decreased frequency, decreased energy. And I'll show you what I mean by that in just a second, but I'm going to erase this. Okay, so wavelength, frequency, inverse relationship between wavelength and frequency, and then direct relationship between frequency and energy. Now, what do I mean by that? These photons that we're talking about, you have to realize that when they're talking about the photons, that's what's actually coming out of the tube to make the exposure. Okay, so when you talk about the X-ray photons in the tube, right? Let's say you have a tube that looks like this, and these are your collimators on the tube, and these would be like your handles on the tube that you hold on to and move it over the table. Well, what comes out of here is photons. Your X-rays, your beam comes out, and there's different energy values in that beam. And you have one photon. Let me just reference this for you. So these are all the photons that would be in the X-ray beam. And let's just give it one in the middle, like that. In this red one that's kind of hard to see, that red one is called your central ray. Okay? That central ray is an imaginary photon. In the center of the beam that contains 100% of the energy. So central ray is the imaginary photon in the center of the beam that contains 100% of the energy. Now, what energy am I talking about? Whatever you're set at, whatever your control panel is set at. So let's just say the control panel on this is set to 80 kVp. Okay, each of these photons is in this beam. So we'll call this the primary beam. So when you radiate a patient, all these photons are in the primary beam, meaning when you make that exposure, all of these go towards the patient. But what they're made up of is different energy values, because that's one of the things that Rankin first realized, is that not all the photon energies are the same. They're all different. It's polyenergetic, meaning multiple energies. So essentially the one in the center has 100% of the energy, but all the other ones have different energy values. So why do we care about that? Because when we look, if you look at these with regard to the wavelength, they're all different, correct? If you look at the wavelength of these, they're slightly different. The frequencies are different. So what does that mean? Different energy values. This one has the most energy. It would roughly have 80 kilovolt potential behind it, whereas this one has less energy. How do we know that? Because the wavelength is longer and the frequency is less. So when they come out like this, something like this, has less energy than something like this. What does that mean? What does that correlate to? This is more penetrating, okay? More penetrating. So if we erase all that, and we just look at 2 to simplify it. All right, if we have 2 photons and one comes out like this, and one comes out like this one is more penetrating, meaning it's going to go through the part better, has more energy, has a shorter wavelength, and it has an increased frequency. Whereas this one is less penetrating, it has less energy, it has a longer wavelength, and it has a decrease in frequency. Now, with that being said, what we just said holds true, right? That frequency and energy have a direct relationship, because more would mean it's going up and less would mean going down. So frequency and energy have a direct relationship. Frequency and wavelength, this is longer, which means it's going up, and that's going down. So they're inversely related. Same with here. This is a shorter wavelength, so it's going down, but an increase in frequency. So those are inversely related. Okay, but remember, when we talked about the wave-particle duality theory, we said that we can describe them like waves, right? Or like particles. So if you want to talk about the wavelength and the frequency, that's fine. You can do that with these photons, but we tend to talk about them with regard to how they interact with matter, more like more like particles, because we talk about things that, as far as how penetrating is it. I need more to go through the chest. Why? Because the chest is thicker, there's more in there, versus a hand. The hand is very thin to be able to go through, right? So you don't need as much penetrability here, but you need a lot more here, a lot more in the abdomen, because anytime you're examining the trunk, it's a thicker part, more dense, made up of more composition, so you need more oomph to get through that. So you need something like this. But the beam itself is polyenergetic. We can't change that. We can filter out the low energy photons so that we have the strongest ones getting through. But realize that with regard to energy, that determines if you get black on your image or you get white, right? Because if something is very penetrating, if it's like this, then it's more likely to go through the part. So that might give you black on your radiograph, or that would correlate to exposure, right? That's your exposure. Whereas if something doesn't go through, if it's kind of wimpy and weak, that is more likely to get absorbed in the patient and not go through. So if nothing is there to strike the image receptor, that's how you get your white on your image, which basically is a lack of exposure. Hopefully that makes sense. When something's more likely to go through, it's going to leave a mark on the image. It's going to make an exposure, an area of dark or black. But if it doesn't go through, then there's nothing left on there, right? So we need more energy, more penetrability to go through thicker parts, denser parts. That's why this gets absorbed in bone and does not show. This tends to blow through like lung tissue, air, things that are more radiopaque. This is things that are more radiolucent. This will blow through something that is more, how do I say that? Maybe I screwed that up. When you have something that's more radiolucent, it's more likely to blow right through and give you black. When it's thicker and you don't have as much energy to go through it, it's more likely to come up white because there's a lack of exposure and it's been absorbed. Okay? All right, let's move on to one more thing that I think you might have found confusing in that chapter. And that is the inverse square law. Because I told you that I would break that down a little bit easier. So I do need a calculator. Oh, I know. One more thing I told you I would tell you is the difference between an X-ray and a gamma ray. And what's the difference? The difference is their point of origin. Okay, so if you had the nucleus of an atom and you had the orbital shells, okay, and gamma ray comes from the nucleus of a radioactive atom. So if you had a gamma ray, you would literally see it coming from the nucleus. That would be a gamma ray. Nucleus. That's the nucleus. When you have an X-ray, X-rays are created on the orbital shells. So an X-ray photon might look the same way, but it's coming from the shell. So this comes from the shell. The gamma ray comes from the nucleus. And the book says that we know we can't see them, but if you were able to see them, the only way you would know the difference between the two was if you saw where it started or where it originated. If you don't know where it originated, then there's really nothing to tell you what's the difference between an X and a gamma, because they both have the ability to ionize matter. We tend to see gamma in nuclear medicine and radiation therapy. We use X-rays in radiation therapy. We use it in diagnostic radiology as well. So unless you see the point of origin, you cannot tell the difference. The only difference is where they originate. Gamma comes from the nucleus of a radioactive atom. X-rays come off the shell of an atom. All right. Now we will look at the inverse square law. But before we do any kind of math, I always like for you guys to dissect the formula, because the formula is the key in all of this. So inverse square law mathematically looks like this. I'm going to start up higher so we have more room. Okay, it's I1 over I2 is equal to D2 squared over D1 squared. Okay, that's the formula. Now, what do those mean? Okay, first thing, let's look at the I's. I1 is your first intensity. Okay, your first intensity, and I'll talk about something more with that in a second. I2 is your second intensity. What do we have over here? Distances. D2 squared. So D2 squared is your second distance. and that number is squared. And d1, also squared, would be your first distance squared. Okay, so that's the breakdown of what they represent. Now, what am I looking for? Intensity. Do you remember that typically I tell you guys that intensity has to do with quantity, and typically when we think of that, we think of exposure. Okay, so intensity is your quantity or the number of exposure. So when we look at things like our intensity in a problem, we're looking for specific qualifiers. We're looking for things like the radiologic units, like the Rankine, the coulombs per kilogram, the rem, the rad, the gray, the sievert, and then you could also add milli to any of those. Okay, so little m, capital R would be milli Rankine. Little m, capital G, lowercase y, milli gray. All right, so those are your intensities. So anytime you see intensity, you're looking for these kind of values to plug in on this side of the equation. Distance. When you think of distance, what do you think? Measurements, right? So what are we looking for? We're looking for things like inches, feet, centimeters, yards, anything like that that references a distance. That's what you're going to look for to plug into the equation. Okay, so you got to understand the equation, and it's an inverse square law. Inverse square law. So when you think of inverse square law, D2 goes on top, D1 is on the bottom, so it's kind of flipped. That's why they call it an inverse square law. And the inverse square law, by definition, says that radiation intensity spreads out over a greater distance, meaning that the farther the distance is away from the source, then you have less exposure in that area. Like if you think about the sun. If you live closer to if you live up on the mountains where you're closer to the sun, right? The closer you are to the sun, you tend to get more exposure from the sun. But if you live down low where there's hardly any elevation, if you live closer to sea level, you're still going to get exposure from the sun, but not near as much as if you lived up on top of the mountain. Why? Because the source would be the sun, and the closer you are to the source, more exposure. The farther away you are from the source, you get less exposure. Why do we care about this in radiology? Because in radiology, when you're closer to the source, you're going to end up getting more exposure. The farther you are from the source, you get less exposure. So for us as technologists, if we can take one step back, we get much less exposure than if we're right up next to the source. So that's important. So this mathematical formula tells you how to figure out either the distance or the intensity that you would get at a specific distance. So I'm going to erase this, so make sure you wrote all that down, and I'm going to show you what I mean. I'll give you a couple word problems that will work out together. Okay? I'll put the formula back up just so you can make sure that you're getting that correct. All right, so let's put the formula up. I'm going to kind of write it small. I1 over I2 equals D2 squared over D1 squared. All right, now let me give you a word problem. Let's say, I'm going to write small. I'm warning you just because I am going to show you how to figured out where to plug it in, and then I'm going to do the math. So I'm going to write kind of small. So let's say a radiologist stood 2 feet. No, that's too far. Let's say a radiologist stood 10 inches from the fluoro tower and got a badge reading, like his OSL, his badge that he wears to tell how much exposure he gets, got a badge reading of 412 millisievert, right? Because, nope, take that back, not millisievert. Occupational dose, I was right, occupational dose is expressed in REM, radiation equivalent man, and the SI equivalent to that would be a sievert. So let's say he got 412 millisieverts. And then, so he stood 10 inches from the tube, got a badge reading of 412 millisieverts. If he moved to 16 inches away,